All right, so now we're going to talk about molecular geometry, or the shapes of these covalent compounds, and we're going to deal with the 3D shapes of these covalent compounds and the different types of shapes, as well as how we get those shapes. Now, before we get into those molecular geometries, you first remember you need to know how to draw these Lewis structures. So here's the steps to drawing these Lewis structures. If you can't draw the Lewis structure, you're not going to be able to predict the molecular geometry. So what the Lewis structures are going to tell us, they're going to give us how these atoms are going to be connected between each other. Right? So what atom is physically connected to another with what type of bond? Single, double, triple, how many lone pairs do we have, that sort of stuff. Okay? The shape or molecular geometry of the molecule that we're talking about is going to be determined by its bond angles, the angles between those different bonds around that atom. Those bond angles are going to be determined using something called VSEPR, or valence shell electron pair repulsion theory. Right? So in a molecule, those valence electrons are going to be involved in bonding pairs. They're forming those bonds between atoms, as well as lone pairs. Right? And the way those are going to work is they're going to orientate themselves to maximize the distance between them, or to minimize their interactions. Remember, we're dealing with electrons. They have a negative charge. Whether it's a bond or a lone pair, those negative charges are going to try to repel away from each other if possible. They're going to get the maximum distance they can from each other. Okay? When we're looking at these things, you're going to need to know the names, structures, and bond angles for all these different types of geometries. You're going to need to know those shapes in order to draw the pictures, in order to understand later on important effects that these have on physical properties of these compounds. Right. Another important thing that you're going to need to recognize is deviations to these overall bond angles. We're going to talk about those later on. Okay, but let's go back to this VSEPR theory. All right. If I look at a central atom here, and I've got 3 atoms surrounding it, and it's got that central atom has a bond between each atom, well, each of those bonds has 2 electrons in it. So to maximize the distance between those electrons, between those bonds, they're going to arrange themselves in this pattern. Okay, we're going to get this repulsion between all of them. And that repulsion can lead us to what we consider 5 basic electron domain geometries. So these are going to be electron domain geometries. These are going to be the 5 main ones. So if I look at my atom and I have 2 areas of electrons, I can picture that as having 2 balloons tied together. If I tie 2 balloons together, what's their maximum distance apart from each other? Well, it's going to be a linear fashion, and their bond angle is going to be 180 degrees from each other. If I take 3 balloons and tie them together, the maximum distance they can get apart from each other is called trigonal planar. The bond angle between those is 120 degrees. Right? The next one, if I take 4 areas of electrons around the central atom. Now remember, these areas can be bonds or lone pairs. Okay, if I take 4 areas of electrons, I'm going to get something called a tetrahedral shape. Okay, when I put those 4 balloons together, that's the maximum distance they can get from each other. If I take 5 areas, that's going to be something called trigonal bipyramidal. With trigonal bipyramidal, we're going to basically take a trigonal planar and a linear and put them together. Okay, so the trigonal planar part is in the middle plane there. Bond angles between those are 120 degrees. And then we have that linear part is at 90 degrees from the trigonal planar part. Then I can take an octahedral, which has got 6 areas of electrons, and everything in the octahedral is going to be 90 degrees from each other. Okay, so let's look at some examples of these, maybe a little bit clearer picture. So I've got my linear geometry. You can see example here is BeCl2. With BeCl2, I have 2 bonds. Those bonds, to get maximum distance from each other, are going to be 180 degrees from each other. BeCl2 is a linear molecule. Okay, if I look at BF3, BF3 has 3 bonds, 3 areas of electrons around it, so that's going to be a trigonal planar. With trigonal planar, all of those atoms are in the same plane. All right, now this is where it gets a little bit more tricky. If I have the 4 areas, that's the tetrahedral. Those are 109.5 degrees from each other. So if I look at CH4, so carbon has 4 bonds around it, that's 4 areas of electrons. Because of that, the maximum distance they can get from each other forms this tetrahedral shape. The bond angle between those is going to be 109.5. Now in this tetrahedral shape, if you picture two of the hydrogens being in the same plane as the carbon, and then one hydrogen is coming out towards you, and one hydrogen is going back away from you. That's kind of the 3D structure for this. So you notice all the atoms here are no longer in the exact same plane like they were trigonal planar. Okay, we've moved out of the plane, and we've got to get to an understanding of these three-dimensional shapes. Lewis structures so far have only showed us two-dimensional shapes, but in reality we're dealing with three-dimensional molecules. Okay. All right, if I go to trigonal bipyramidal, basically trigonal bipyramidal, so in this case my example is PCl5. If I look at the plane there, I've got a trigonal planar part between the phosphorus and three of the chlorines. And then up above that, I've got another chlorine. Well, if I were to look at this, that would almost make like a pyramid. And if you look at that central picture there, just the top half of that trigonal bipyramid, it makes a little pyramid with a triangular base. Okay, well, when I add the chlorine on the bottom, then I get a second pyramid. That's why it's called trigonal bipyramidal. Okay, it's basically two pyramids. The bi part means two, and they've got a triangular base or a trigonal base. Okay, that's where we're getting this from. So with trigonal bipyramidal, we've got a trigonal planar and a linear put together. Octahedral geometry. Well, the octahedral geometry, the name comes from the fact that we have an octahedron. Mainly I've got a pyramid up top that's got a square base to it and a pyramid on the bottom that's got a square base to it. If I look at the number of sides that are formed by that, I get 8 sides formed from those two pyramids. Okay, that's where the octahedral comes from. Main thing with that, everything's 90 degrees from each other. Okay, remember, these are all repulsions based upon these electrons. Okay, these electrons are trying to maximize their distance from each other. And with the number of bonds that we have around that central atom, this is the maximum distance we can get. Now, something that's going to cause deviations in these bond angles, though, is going to be non-bonding electrons as well as double bonds. But let's first consider non-bonding electrons. Well, if I look at a bonding electron pair, it's between two nuclei. There's a bond there. So those are kind of contained a little bit better than if I just look at a lone pair of electrons. The lone pair of electrons aren't bound between two atoms, so they actually are going to give up a little bit more of a repulsive force. They're going to, if you will, take up a little bit more space. Because they're going to take up more space, they're going to push other bonds away from them. All right, so if I start with CH4, which is tetrahedral, I can see two hydrogens are in the same plane as the carbon. One hydrogen is coming out. That's that little wedge shape there. The little dotted dashed line shows that hydrogen going back and away from you. Okay. In tetrahedral, everything's 109.5 degrees. If I go to NH3, with NH3, it's got a lone pair at the top. Well, now that lone pair takes up more space than that top carbon-hydrogen bond did. And so what happens is all of those nitrogen-hydrogen bonds get forced closer together, so they get a smaller bond angle. All right, now you don't need to know it's exactly 107 degrees. You just need to know that it's going to be less than the 109.5. If I go to water, because it has two lone pairs, I get an even smaller bond angle. Okay, so when I have non-bonding electrons, that's going to change the bond angles that we see. It's going to cause the bonds to be pushed away from those lone pairs more and cause a decrease in those bond angles. Now, another thing we have to worry about then is double bonds. If I have a double bond, that means I have more electrons there. Well, more electrons means it's going to have more electrostatic repulsion. So wherever I have a double bond, it's going to push other bonds away from it further. So if I were to look at this COCl2, well, initially it would start in a trigonal planar shape because I've got 3 areas of electrons around that carbon. Okay, and keep in mind, when I talk about areas of electrons, a single bond counts as much as a double bond or a triple bond. Okay, anywhere there's a localized area of electrons between two atoms, that counts as one area of electrons. So around the carbon, I have 3 areas of electrons. That should be trigonal planar, should be 120 degrees. But because one of those is a double bond, the double bond pushes those carbon-chlorine bonds further away, so the angle between the carbon-chlorine bond and the carbon-oxygen double bond gets larger than 120 degrees. And the carbon-chlorine bonds get pushed closer together, so it becomes less than 120 degrees. Okay, so those are some things that are going to affect those bond angles. All right, let's go back to looking at geometries. So we've talked about the 5 basic electron domain geometries. Now we're going to talk about actual molecular geometries. And you need to recognize the difference between those. Electron domain geometries, there's going to be 5 of them. Molecular geometries are going to take into account whether areas of electrons are bonding electrons or non-bonding or lone pair electrons. If you look at the first row, number of electron domains, I have 2. The electron domain geometry is going to be linear. Bonding domains, I have 2. Non-bonding domains, I have 0, so the molecular geometry is linear. So in that case, the electron domain geometry and the molecular geometry are the same. Example of that is CO2 gas. If I go to where I have 3 electron domains, well then my electron domain geometry starts in trigonal planar. If all 3 of those electron domains are bonds, then I end up with a molecular geometry of trigonal planar. If one of those electron domains is a lone pair, I end up with what we call a bent structure. So now we need to break these down from just their electron domains into these more specific molecular geometries. Okay, so linear is always linear. Trigonal planar could be trigonal planar or bent, depending upon how many lone pairs you have. Okay, if I look at the tetrahedral geometry, well, with the tetrahedral electron domain geometry, if all 4 of them are bonds, I end up with a tetrahedral molecular geometry. So around this nitrogen, I have 4 areas of electrons, so I start with electron geometry of tetrahedral, but because one of them is a lone pair, we're going to call that trigonal pyramidal. All right, why is it called trigonal pyramidal? Well, if you look at the way that's situated, those 3 hydrogens aren't in the same plane as the nitrogen. Okay, that nitrogen is sitting up a little bit. Because that nitrogen is sitting up a little bit, it forms a little pyramid, where the nitrogen is the apex of the pyramid. The 3 hydrogens are the base of the pyramid. Those 3 hydrogens form a triangular base, so trigonal pyramidal. Don't confuse this with the trigonal bipyramidal electron domain geometry. Okay, this is trigonal pyramidal. We only have 1 pyramid. This is a molecular geometry coming from that tetrahedral electron domain geometry. Now, keep in mind with this, because we have that lone pair, ideally all those bond angles would be 109.5 degrees, starting with that tetrahedral electron domain geometry. But because we're actually dealing with that trigonal pyramidal, which has a lone pair, that lone pair pushes all those bonds away, so we end up with less than 109.5 degrees. All right, what if we go to water? Water has 4 areas of electrons around it, 2 bonds and 2 lone pairs, so its electron geometry would be tetrahedral. Because we have 2 lone pairs, though, its molecular geometry is going to be called bent. Okay, now because we have 2 lone pairs, the bond angle with that is going to be even less than the 109.5 degrees. Okay, so just to summarize these tetrahedral electron domain geometries, if I've got no lone pairs, then it's going to be a tetrahedral molecular geometry. If I've got 1 lone pair, it's going to be trigonal pyramidal. If I've got 2 lone pairs, it's going to be bent. If I look at this table, this summarizes it here with those examples. All right, so you need to keep straight electron geometries and molecular geometries and the difference between those. These are all the same electron geometry, but they're all different molecular geometries because they have different number of lone pairs. Okay, and we're going to see that with these others as well. All right, so let's look at trigonal bipyramidal. Trigonal bipyramidal, I have 5 areas of electrons. If all 5 of those areas are bonds, then my molecular geometry is going to be trigonal bipyramidal. Now, when I go to add electrons onto a trigonal bipyramidal system, they're always going to add onto the trigonal planar part. They're never going to add into that linear part. Okay? Linear part is what we're going to call axial. Trigonal planar part is what we're going to call equatorial. So as we go to add lone pairs onto that trigonal bipyramidal electron domain geometry, they always go on the center. So if I add 1 lone pair onto my trigonal bipyramidal electron domain geometry, I get a seesaw molecular geometry. Okay, so the lone pair is coming off of that sulfur. All right, now why is this called a seesaw? Well, if I turn it on its side, I could rock those fluorines back and forth like a seesaw. That's why it's called a seesaw. Okay, if I make 2 of those lone pairs, remember electron domain geometry, I have 5 areas of electrons. That's trigonal bipyramidal. 2 of them are lone pairs. It's now going to be called a T-shaped. Why? Well, because it looks like a T. Okay, if I go to 3 lone pairs, then it just becomes linear. But this linear is going to be different than the original linear because this is starting with electron geometry of trigonal bipyramidal. Its molecular geometry is linear. Okay, bond angles are going to be the same, but you need to distinguish these because this particular linear molecular geometry is going to have 3 lone pairs on it. Okay, then a table just to summarize those. So again, all of these have the same electron domain geometries, but they're going to differ in their molecular geometries, and that's going to depend upon how many lone pairs we have. So all of these are trigonal bipyramidal. However many lone pairs we have determines the molecular geometry. Okay, then we can go to octahedral. Octahedral has 6 areas of electrons. If all 6 are bonds, then we have an octahedral molecular geometry. All right? One of those is a lone pair. We're going to call that square pyramidal. Why? Well, because it's forming a pyramid with a square base. Now, when I go to remove a second bond and replace it with lone pair electrons, when I go to do that, it's going to be opposite of my first lone pair. In other words, I'm not going to take any off the planar part. I want maximum distance between these lone pairs of electrons, and to do that, those lone pairs have to be opposite of each other. So, when I get to 2 lone pairs on an octahedral electron domain geometry, that becomes something called square planar. All right, so here's a table that summarizes all those. So, all of them, electron domain geometries are octahedral. They just differ in molecular geometries depending upon how many lone pairs we have. Okay, so here's just another picture that helps kind of put all of them together. So remember though, we have those 5 basic electron domain geometries. Each one of these boxes represents one of those 5. So linear, trigonal, planar, tetrahedral, trigonal, bipyramidal, and octahedral. And then those can be broken up into sublevels called the molecular geometries. All right, you need to know both.